This is Engineering Statistics and Linear Algebra. We are in the module 2. And in the module 2, in the last class, we finished the independent random variables. Whenever the multivariate or bivariate random variables are there, whenever they are independent, what really happens? Okay, today we will take up what is known as multivariate, PDF. This is density function. Density function just corresponds to the probability density function. So we know that the probability density function is the differential of the cumulative distribution function. Okay, the probability density function is the differential of the cumulative distribution function, and if we take the multivariate case, then the probability density function of the multivariate, what you call of many variables, PDF of many variables will be equal to the, so to say, nth derivative of the CDF, or you need to differentiate here partial derivative for each of the different variables corresponding to, with each of the different variables corresponding to the CDF. Inversely, taking it inversely, we can write the CDF of a the multivariate random variables will be equal to the what you call integration. This integration will be again corresponding to each of the different variables we have considered. If you have n variables, then the number of times the integration is to be done will be n of the multivariate PDF. Okay, this is the multivariate PDF whose integration is to be taken, and we will get the multivariate CDF. So multivariate CDF is equal to the integrations for each of the different variable of the multivariate PDF. Similarly, the multivariate PDF is the differentiation with each of the different variables of the multivariate CDF. Okay, so they are the inverses of each other. Okay, they are the inverses of each other. Further to that, if we take the limits here x1, x2, x3, xn to be infinity, 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 then we will get this function, that is the total area, the total area or volume or whatever you call it for the n dimensions. So this will be n dimensions corresponding to x1 to xn. Okay, under the probability density function of a multivariate random variable will be equal to 1. If you're taking only one variable, then integral of minus infinity to infinity small f x x will be equal to 1. Now we are taking here many different variables, so therefore multiple integrals with each of the integral having limits minus infinity to plus infinity of the multivariate PDF will be equal to 1. So this condition of 1 should be satisfied. Okay, this condition of 1 should be satisfied. So with this, assuming that, considering that the PDF and the CDF are inverses of each other, that is, PDF is differentiation of CDF, CDF is integration of the PDF, also area or volume under the what you call PDF will be equal to 1, whether it is 1 dimension or 2 dimension or 3 dimension or for that matter n dimensions, right? So let us take some of the examples associated with it now. So in the chapter 3, exercise 3, if you take the joint PDF fxy x comma y is equal to c is a constant. Okay, fxy, that is the PDF value, the multivariate or bivariate here because we are taking xy, bivariate PDF is a constant c between the values 0 less than x less than 3 and y between 0 and 4, x between 0 and 3, y between 0 and 4, and is 0 otherwise. So what is the value of the constant c? What are the PDFs for x and y? What is f of x, the CDF here, again within the same limits. Again, what is the CDF when we don't consider the variable y, that is, we take it infinity here, and when we don't consider the variable x, and that is, we consider infinity over here. Are these two values, x and y, variables independent of each other? That's what we need to consider. So first is, it's a constant c. Okay, it's a constant c between 0 to 3 for x and 0 to 4 for y. So naturally, there are two variables here. So double integration of this, double integration of this between the limits 0 to 3 and 0 to 4 for x and y. Okay, for x and y will be equal to 1. Okay, double integral of the PDF will be equal to 1 if we take the total limits minus infinity to infinity. Out of that minus infinity to plus infinity, only 0 to 3 for x and 0 to 4 for y exist. In the other places it is 0. That's why we have this integral 0 to 4, 0, integral again 0 to 3. Now this 0 to 3 is for x, 0 to 4 is for y. Okay, c is the value of the what you call probability density function, dx dy. Okay, if you integrate this, okay, it will become cx with limit 0 to 3, that is 3c. Then later again, if you integrate this, it will become 3cy with limit 0 to 4, and that will give us 12c, right? 12c will be equal to 1. Therefore, c is equal to 1 by 12. So this is, rather, what is given to us is a uniform distribution. Uniform distribution with a value c equal to 1 by 2, with values of x between 0 to 3 and values of y between 0 to 4. Okay, c value is 1 by 12 now. Now, how can we find the PDF for x and y? And that can be done by considering, the value itself, the c value itself, or rather, I should take this and integrate it with respect to y 0 to 4, then I'll get fxx. Okay, integrate it for y 0 to 4, the value of f of xy, then you'll get f of xx. That means fxx is equal to integral, okay, the limits of y, that is, might be, you can write it as minus infinity to plus infinity of y. Okay, fx y x comma y dy. Okay, this value will be integral of this dy. The value of fyy will be integral of this dx. Okay, so if you take that, the value of this is again cc. We already found it as 1 by 12, and that's why that is taken integral 0 to 4, limits of y is 0 to 4 dy, and that gives us the value 1 by 3. Similarly, fyy is 1 by 12, 0 to 3, the dx, and this is corresponding to the limits of x over here, and that will give us 1 by 12 into 3, that will be 1 by 4. So within the region 0 to 4. So y will be within the region 0 to 4, x will be the value between 0 to 3, and integration should be the other way around, that is 0 to 4 in this case and 0 to 3 in this case. Then we can try to find the CDF over here. The CDF will be the what you call integration of the so to say CDF. We know very well CDF how we have written. We have written like this. So minus infinity to x1, minus infinity to x2, minus infinity to xn of the PDF. Okay, so we have two variables only, therefore it will be two integrals for that. So two integrals, then the PDF we need to write, and that PDF is C. C is again 1 by 12, therefore 1 by 12 is taken out, and we are writing here 0 to x and 0 to y du dy. And if you integrate this, you'll get y. If you integrate this, you'll get x. So xy by 12. Xy by 12 is what you'll get. Again, within the range which is there over here only. Okay, within the range which is there here only. So now we can go for finding the CDF only for a single variable. For a single variable, that is fxx will be fxy x comma infinity. That is what we have over here. This is no y variable, therefore it will correspond to x variable only, and that is fxy. The CDF with the value of y considered as 4. Now there's no more infinity because the value of y exists only between 0 to 4. In the other region, it doesn't exist. So whether I write infinity here or 4, it doesn't matter because y is within the range 0 to 4. So considering that, if you take over here the value xy infinity divided by 12, this y will be the value 4. The y value will be 4 here because it is existing only between 0 to 4. So x into 4 divided by 12 will give us x by 3. Similarly, fyy will be fxy infinity y. So x value is infinity. Infinity means again, all the values do not exist. So therefore, we'll write here 3. Okay, fxy 3 comma y. And if you substitute 3 in this xy by 12, you'll get y by 4. Okay, then we can just try to multiply to test whether they are independent at all. We can multiply these two. We will multiply 1 by 3 and 1 by 4 will get 12. And that 1 by 12 itself is the value which we already have here. So 1 by 3, 1 by 4 will give us automatically the value which is this c 1 by 12. Okay, fx y x comma y is 1 by 12 because c we have found it as 1 by 12. Okay, so thus we can say that fxx fyy is equal to fxy x comma y, and because they are separable, we say that they are independent. Okay, because they are separable, we say that they are independent. Okay, we'll go for the next problem. A bivariate PDF for the discrete random variable x and y is given by 0.2 del x del y plus 0.3 del x minus 1 del y plus 0.3 del x del y minus 1 plus c del x minus 1 del y minus 1. So this is discrete. Now earlier case we had a continuous random variable, but now we have the discrete case. What is the value of the constant c? What is the value of the constant c? So this is a bivariate PDF. So again, we need to integrate this over here. It should be a double integral for both the cases, and that will give us, the value of the c. Okay, if you take it, you'll get the value c. Or rather, one can say that if you double integrate it, then you'll get it as 0.2 plus 0.3 plus 0.3 plus c is equal to 1. Okay, if you double integrate it, you'll get 0.2 plus 0.3 plus 0.3 plus c is equal to 1, because double integrate in the whole range, it should be equal to 1. Total probability should be equal to 1. Total probability should be equal to 1. If you integrate the PDF, you should, in the overall region, you should get the value equal to 1. That is the total probability. Okay, so thus you'll get 0.2 plus 0.3 plus 0.3 plus c is equal to 1. So c is equal to 0.2 plus 0.3 plus 0.3 will be 0.8. So c will be equal to 1 minus 0.8, and that will give us the value of c equal to 0.2. Okay, that will give us the value of c is equal to 0.2. Then what are the PDFs for x and y? So again, it's going on the same way. fxx is equal to single integral of f of xy x comma y dy. Okay, so if you integrate it with respect to y, this y terms will go, this y term will go, and this y term will go, and this y term will go, and this y term will go. So we are left with the del x term here and del x term here, 0.2 plus 0.3, that will become 0.5. We are left with x minus 1 term here and x minus 1 term over here. This is 0.3, and c we have just calculated 0.2, that will be 0.5. So 0.5 del x plus 0.5 del x minus 1. Integral of del x, please remember, integral of any quantity, del will be equal to 1. Integral del y dy will be equal to 1. Similarly, integral del x dx will be equal to 1. Okay. However, integral del x dy will not be equal to 1. Please remember that, because we are not trying to what you call, you can't say the variable, the what you call impulse is with respect to x, and we are integrating with respect to y, and the integral of that is 1. No, it cannot be. Only integral of del x dx will be 1. Integral of del x dy, del y dy will be 1. Integral of del x dy will not be equal to 1 because the integration is with respect to totally a different variable. Okay, so here we have both the quantities del x, del y, but when we are integrating with respect to dy, only the del y will vanish because the integral of that del y will be equal to 1, and we are left with 0.5 del x plus 0.5 del x minus 1. Similarly, to find fyy, we need to integrate the bivariate PDF with respect to x, So all the del x terms will vanish from here. What we will be left with is 0.2 del y, 0.3 del y, 0.3 del y minus 1, 0.2 del y minus 1. So again, it will be 0.5 into del y plus 0.5 into del y minus 1. Okay, so fxx and fyy will be these two quantities. Now we need to find the value of the CDF. The CDF can be found from the PDF over here. This is the PDF. F of xy, that can be found straight away from the formula which is given over here. So now, because we have two variables, it will be double integration. Limits will be, please remember, minus infinity to x1. The time you put minus infinity to infinity, the whole thing integral will become 1. But if you put minus infinity to x1, minus infinity to x2, then it will become the CDF. Okay, so that is the different thing which we should make out. Okay, so now if you do this over here, if you integrate this with respect to both this and this, with respect to the value limits x and y, okay, between the range 0 to 1 and 0 to 1 again over here, okay, you will get as the value which will be straight away equal to 0.2 itself. You can just integrate that, you will get it as 0.2 itself. Okay, between 0 to 1 and 0 to 1, these are the limits which we should consider, x and y. So that means integral 0 to 1, integral 0 to 1, this whole thing over here, okay, dx dy, okay, you will get the value as the value which just corresponds to 0.2. Okay, 0.2. You can try this exercise, right? Then fxx will be, you integrate this over here, you substitute this over here with y equal to infinity in the similar way which we have done over here, right? And y equal to infinity means, again, we should consider within the range which is given there for us, and that will be the value which will be 0.5 ux plus 0.5 ux minus 1. Okay, 0.5 ux plus 0.5 ux minus 1. Okay, so within this range, if you say, then we need to write it correspondingly for that value. Okay, so within that range means we should try to write within that condition. Similarly, fyy will be in the same way. We can write it with the value being substituted from the fxy over here, or you can take only for the single variable, just means you can take this quantity and integrate it only with respect to y. You will get the value over here. Take this and integrate it only with respect to y. You will get that, and that will be again, if you integrate it, then naturally what you call del x is going to become ux. So wherever you have this quantity, if you take this over here, right, this, if you integrate, we know that the what you call CDF is the integration of the PDF. The PDF is the differentiation of the CDF. So best thing to find this is take this over here and integrate it, okay, within the proper limits. So del x will become ux. So del x minus 1 will become ux minus 1. That's all. So each one of this will become u, and ux minus 1, ux and ux minus 1 when we talk about the CDF. Similarly, FYY will be, you integrate this over here, okay? That means integration of del y, okay, will be the value which will be uy within the limits 0 to, so to say, y1, within the limits 0 to y1. Differentiating between 0 to infinity will make it 1. Differentiating, integrating between 0 to y, infinity del y will make it 1. Integrating del y minus 1 between 0 to infinity will make it 1. But integrating between 0 to y, del y will give us the value, integrating the impulse function between 0 to y will give us the value which is the, step function ux. Okay, so this differentiation you should be able to make out. Integration in the whole of the interval, if I have del y will be 1. But integral in only between some range will give us the unit step function of the impulse function. Similarly, differentiation of ux will give us the what you call impulse function. Ux is the what you call step function. Differential of that will be the impulse function. So thus we can find these two. Now if you try to multiply these two over here, okay, this and this, we'll get 0.25 del x del y plus 0.25 del x minus 1 del y, 0.25 del x del y minus 1 plus 0.25 del y minus 1 del y, del x minus 1 del y minus 1. Now this is not the one which we have for f of xy, because f of xy is this with c is equal to 0.2. Okay, here we have 0.2, here we have 0.25, here we have 0.3, here we have 0.25. So it cannot be same. So they are not same, and hence, x and y are not independent. X and y are not independent. So we will go for the numerical, which is question number 5. Right? So now we are given the value of f of xy. This you can see that it is continuous, right? This is continuous for values of both xy between minus infinity to infinity, and you can see that this is, somewhere similar to your, Gaussian function. Might not be exactly Gaussian, but it looks like Gaussian. So what are the PDFs for x and y? Okay. So is 3.12 satisfied? Are x and y independent? Okay. So these are the different things he is asking, right? So what are the PDFs for x and y? So PDFs for both the x and y together is found over here. So we need to find the PDF for x and y separately. Okay, separately. So we can try to write the x squared minus 0.6xy plus y squared as x plus 0.3y whole squared plus 0.91 y squared. Okay, as the squared terms, we can try to write like this, and also we can write in the other way around, right? That means you can try to write it as, similarly, y minus might be 0.3x whole squared plus 0.91 x squared. Even that also can be written. This is equal to y minus 0.3x whole squared plus 0.91 x squared. Okay, that also is possible because this is symmetrical. You can see that this is a symmetrical equation. So therefore, it is equal to this, as well as y minus 0.3x whole squared plus 0.91x squared. Okay, you can write that down also. So now you can try to find fyy over here is equal to integral of minus infinity to infinity fxy x comma y, and this is just nothing but this. We should substitute from here. So if you substitute from here, okay, then we are trying to differentiate, integrate it with respect to x. So y term can be taken out. Okay, whatever y term is there over here can be taken out over here. This y term is taken out over here, right? Plus 0.91 y squared, that will be becoming minus because of the reason that we have a minus here, right? So this is taken out over here, okay? 1.82 is also taken out over there, and this remains as it is. and what we are left with is this term, and that we are trying to write it over here. So if you try to integrate this with respect to dx, okay, only x term is there over here, then we'll get 1 by root of 2 pi e to the power of minus y squared by 2. This can be integrated. Okay, please try to integrate this and check whether you'll get this same thing at all. Okay, similarly, you can write the other one which I have told you, that is y minus 0.3 whole square plus 0.91 x squared. Substitute that in the f of x comma x equal to integral minus infinity to infinity f of xy x comma y dy. This will be same thing over here, except that this will be dy. This will be same thing as this, except that it will be dy over here. So this, in place of this, you can substitute the term which I have told, this, and in place of this, whatever I have told you here, that has to be substituted, and then you try to integrate. So naturally, in place of this, it will become f of x will become, this will be x squared. Okay, this will be x squared, this whole term remaining same, and this will be y minus 0.3 x whole squared by 1.82, and that will give us e to the power of minus x squared by 2, and this quantity will be 1 by 2 pi. Okay, so this is how we can try to solve, right? So the second part is the 3.12 satisfied? You can say that if you integrate this over here within the whole of the limit, whether it is this or this, okay, that's what he's trying to do over here, both will turn out to be 1. That means total, so to say, the what you call probability should be equal to 1. Double integral of this 3.12 is nothing but, I think, double integral of the PDF is equal to 1. Right. Double integral of the PDF is equal to 1, is 3.12, and that will be single integral of each one of the fx x or fyy, fxx or fyy, right? So this will be, naturally, you got here fxx and you got fyy. So if you integrate it once between minus infinity, that will turn out to be 1, because that will correspond to straight away Gaussian. So that means this is the two-dimensional Gaussian distribution function. Now if you multiply this with this, you are not going to get this. So therefore, the x and y are not independent of each other. X, y is not independent of each other.